Okay. 2.6 is called competing function model validation. So model validation has two parts. One is we're going to try to figure out which model is the best. That's the part we've already done. Okay. And then we're going to start to say how valid is this model. Okay. So we're going to use something called a residual score to figure out how valid it is. Okay. So when we determine the model of this, we already know. Okay. So we're going to need at least 3 points to figure this out because we need to do the difference, right? On quadratic, you need 4. So linear, you're looking for the first difference to be the same. Exponential, we're looking to see that we multiply the same thing each time. And quadratic, second difference the same, okay? The other thing is that quadratic is the only one that can repeat a y. So like when you start to see the same, like if you see a linear, obviously your y is not going to repeat because it would have to come down and come back up again. And when you see exponential, it's going to increase. So obviously we know what a line looks like. A line looks like this, okay? Exponential could look like this or could look... But either way, those both only have each y one time, whereas a quadratic, because it's shaped like a parabola, can have a y repeat. It's the only one of the 3. We know how to do this. It says what type of model is represented by the data. So what am I looking for?
For the x to not repeat with...
No, that's if it is. We already know it's a function, right? If we're trying to figure out which type of model.
If the y repeats twice, then we know it's a quadratic.
Okay, but how else?
So the difference.
The first difference, the second difference, and then multiply. So if I wanted to find these differences, right? 2.75 minus a negative 0.75. And I get 3.5. Then 6.25 minus 2.75. 3.5 again. Check it one last time. 9.75 minus 6.25. 3.5 again. So that first difference is the same, which makes this linear. Is the rate of change 3.5? No, why not?
Because you have to divide it by 2.
Good, the x values are going by 2. So if I wanted the slope or the rate of change on this guy, I'd have to divide by 2. Okay, go to B. Let's do it again. 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7. First difference is not the same, right? Then I go second difference. 5 minus 3 is 2. 7 minus 5 is also 2. Makes this quadratic. We sure did. We're just going to keep going with it. Then the last one. Okay, now look at your y values. They're jumping by a lot, right? So instead of even trying the difference, I would see if I could multiply by the same thing. And because maybe with a decimal it makes it a little bit harder, I would jump to the ones that are easy. Like 12 divided by 3 is 4, and 48 divided by 12, is also 4. So is 3 divided by 0.754. I could go the whole way through, right? This is also 4. The rate of change, right, would also be. And the rate of change on these may not be consistent. The only one that has consistent rate of change is a linear function, right? So if I wanted a rate of change on this guy, I'd have to tell you on what interval. So this is exponential. And if we were to describe it, which will come back when we get into logs, it's going to say, how do you know as your input values are increasing, your output values are proportional is the word you'd be looking for. Okay, so this is what's new, and it's called a residual plot. The distance from the actual point to the point on the regression model, okay, these little dots are called, well, that plot is the residual plot. So if you look at these two shapes here, first of all, okay, let's look at these two graphs. This graph says the cost of the meal versus the number of guests. So this is your regular graph. The x-axis is the number of guests. The y-axis is the cost per meal. The dots are your actual data, right? And then they ran a line, a linear function, regression, and that's the green line, okay? So this is what they would use to best fit this model. Now, if you take that green line, which is your predicted line, and you put it on the x-axis, you're creating a residual plot. The x-axis is the line, and all the dots are the distance from those dots to that line. So if this dot is above my model by 5, let's say, then over here, this dot should be above my model by 5. If this dot is below my model by 10, then over here, that dot should be below my model by 10. So the distance between the x-axis and the dots on a residual plot is called R. The order goes actual minus predicted. So the R equals the actual data minus the predicted data. And I remember it because A comes first. Like when I think, is it actual minus predicted or predicted minus actual, I just remember A comes first. So it's actual minus predicted. Now, let's talk about how we're going to compare this. If my model is the line that's of the x-axis, right, and the dot is above it, then I would say the model is an underestimate at that spot. If the model is above the dot, then I would say the model is an overestimate at that spot. So I'm going to go to 2 because 2 only has 1 dot on it. The model over-predicted at 2. And if you go over here at 2, the line is over the dot. Does that make sense? So you have to be able to determine like an R value on both of these types. Okay? Would it be positive? Would it be negative? At 10, the model under-predicted it. Okay? At 4, the model under-predicted it. So think about, where's your line? Is your line under the dot or is your line above the dot? If the line's under, it was an under-prediction. If the line's above, it's an over-prediction. And then R, if you pay attention to the signs, if R is positive, that meant the actual was bigger than the predicted, right? Yes. Which means the model under-predicted it. And if the R is negative, then that meant the actual was smaller than the predicted, which means the model over-predicted. So you'll see this a couple different ways. One, we're about to get an example where you have to like find out what the difference is. But you'll also see something that could just have a dot and it could say, is your R positive 3.5? Is your R negative 3.5? So you have to know positive means the model under-predicted it and negative means it over-predicted it. It would be perfect. There'd be no error there. So if it's exactly on a line like this, it's pretty close. That means then your R would be 0. Yep. And if your R is 0, that means the actual equaled the predicted and the model was perfect at that spot. Yep. The other thing this slide says is that the residual plot, let me highlight it. Okay, if it has a pattern, not that guy, there. If it has a pattern, then it's not appropriate. Not the original graph, so I'm not looking at this original graph at all for that. I'm looking at this graph. If there was a pattern to these dots, if they looked like they were a linear shape or a quadratic shape, or they just took on a strange pattern, but there's a clear pattern, then it's not appropriate. There would have been something better. If it doesn't have a pattern, then it is appropriate. So does it look like this shape has a pattern? No, this model is appropriate. Look how close it is to these dots. That's kind of another way to check. But you won't have both. So here's another example of appropriate and not appropriate. On the left, these are scattered dots. There's no pattern. This would be appropriate. On the right, this looks like it's a pretty patterned shape, right? It almost looks like a quadratic. This would be not appropriate. So is the model appropriate or not? A, is it appropriate? Is there a pattern there?
Yeah,
not really, right? There's a couple dots here, a couple dots there, but there's nothing. It would have to be a very clear visual pattern. So there's no pattern. So this is appropriate, yes?
For it to be appropriate, there can be a pattern.
Correct. So this is appropriate because there is no pattern. Go to B. Is there a pattern?
Yes.
Yes. So is this appropriate? No. Because there is a pattern.
I have a question.
Yeah.
Couldn't it technically be possible that there is a pattern if it's, I don't know, couldn't it?
A pattern typically means that line should have been a different shape because it's taking the R's up at this point, the R's down at this point. It follows. That means there's a different shape that would have been better. Yeah. Yeah.
Isn't that not a function though? Because
well, it's not. This is not a function graph. This is a residual plot. Does that make sense? So this is showing.
It's just like data.
Yeah, it's showing the distance between whatever was originally graphed and the actual dots. So this doesn't have to follow a function test because this isn't a function. Okay, this one says the graph shows a bivariate data set and its least regression squares line. Okay, which graph shows the residual plot for the same data set? So now think that this line, right, became this line in each one. So if the dot was above the line on the top, it should be above the line on these. If the dot was below the line on the top, it should be below the line on these. So the very first one is at 1. At 1, should my dot be above or below the axis? It should be above. So look at 1, under, at 1, under, at 1, over. Okay? If there was another one that was also over, then I'd go to the second one. At 2, should my dot be above or below the x-axis? Below, and it's below. So C is the good one here. Questions on that one? Okay, this is what we already know. So in AP content, it holds the r squared to this point. But I started to say why. Like, why are we doing that if r squareds are what we want to find anyways? So I said that's why I started teaching you earlier, okay? But this is originally where r squared is entered, or is taught. We already know the better, or the closer to 1 your r squared is, the better the model is, right? That's all this says. All right, so this is example, what am I on? 4. The cost of college tuition in the United States has increased by 1,200% since 1980. Consider the average annual tuition and fees presented by the table. Find the model that best fits the data. Compare the predicted cost of the public university in year 2010 to the actual cost, and what does it mean in this context? We're back to explaining. So first of all, our x values, notice it says since 1980. So what would be the x value at 1980? 0. Good. What would be the x value at 1990? At 2000, 20, at 2010, 30, and at 2020, 40. Okay, put it in your calculator, run the regression. All right, so we said based on the r squared, quadratic was best, okay? And this should have been your quadratic model. Remember, make sure it's an equation. It didn't say what the variables had to be, so I just put y. You could have put f of x, whatever, but because it didn't say. So I got y equals 4.673x squared minus 5.334x plus 2008.771. We good on that? Okay. Yeah? Okay, then it said compare the predicted cost of a public university in the year 2010 to the actual cost. Well, if I use the predicted, right, which means I plug in. So I did y1 of 30. And I got $6,054.30. It would be 31 cents because it's dollars, okay? Now I want to compare that to the actual. The actual is the data that was given. So here's my actual, and then the equation gives you your predicted. So what's true when I compare the actual to the predicted? Is actual bigger or smaller than predicted? Smaller than predicted, which means the predicted did what? It over-predicted, okay? The model overestimated or over-predicted. So these are the parts that you have to use when you describe what does it mean in this context. First thing you have to say is when are you talking about? This is not the entire set. This is just in 2010. Then we have to say the model. What did we say? It over-predicted or under-predicted? Actually, we have to find the R, but we'll go back to that in a second. We said the model did what? Overestimated or over-predicted? Over. Either one's okay. Okay. What are they predicting? What's the unit this time? The cost of tuition at a public university by, now what we have to find. How far off was it? And at that point, it doesn't matter if I do actual minus predicted or predicted minus actual because I'm not worried about the positive or negative sign. If it said what is R, I'm worried about the positive negative sign. And I have to do actual minus predicted. Okay? But if I'm just saying how far off it was, I only need the value. So I'm going to do actual minus predicted just so we get used to it. Our actual was 58.14 minus the predicted 54.31. So it over-predicted or overestimated by $240.31. From the other side of the wall. So the different parts you have to make sure you include is what's the input? Did it underestimate or overestimate? What's the output? And by how much was it different? So in order to get the point or complete points for something like that, you have to describe it. This was a question on an FRQ last year and the year before. Not this exact model, but this where it says compare it to the predicted and what does it mean in this context. Okay, one more. Try it all the way through. Quadratic worked again, okay? So the linear should have been y equals 0.229x plus 7.170. Quadratic y equals negative 0.002x squared plus 0.311x plus 6.659. Exponential y equals 7.449 times 1.02 to the x. And from our r squareds, we got that the best model was quadratic. Then it asked you to predict enrollment for 2010, and that was 16.407. Then it wants you to compare it to the actual 2010, which was 18.1. So did the model under or overestimate this time? It underestimated this time, okay? And how much by? Good, 16.4 minus 18.1. 1.693, good.
I have a question.
Yeah.
My calculator's saying like something different.
Okay, I'll compare. Let me finish this one and then I'll come compare. So first of all, this time our r squared would have been negative, right? Because would have been positive because actual minus predicted would have been positive. So if that's part of the question, it's that. I don't need it when I describe it, but if it's multiple choice and it asks you about it, then obviously you need it, okay? So now how are we writing what it means in this context? How do we start? Good. In 2010, good. The model underestimated the number of college enrollments. What's important in that chart?
By 1.693 million.
Before that, though. Oh, you could say that. So if you said by 1.693 million, that's fine. You either have to say it there or you have to say the number of college enrollments in millions. You could say it here. Or you could say it later when you say by, okay? By 1.693, again, you could say it here, million. But you have to include that millions in there, okay? The number of really college enrollments, college. Questions? Not terrible, right? Just one more step, well, a couple more steps. But you've got to make sure we can compare and explain.